Good evening. So we've officially ended Unit 1 last class. Unit 2 is where we get into heavy math. Okay, so in Unit 2, we are going to see these two things here, the Avogadro Constant and the mole. So those are two things that we are going to see in this unit. Understand that some of the concepts that we're going to see in Unit 2, and this carries over from Chapter 6 through 8, will be ongoing in the later units. So one of the things that we're going to be doing later in Chapter 8 is something called stoichiometry. And the concept of stoichiometry carries over into Units 3 and Unit 4, our final unit. So let's find out what these terms are. What is an Avogadro constant? What is the mole? Okay. So 1 mole of a substance contains 6.02 times 10 to the power of 23 of that substance. Okay, that's referred to as the Avogadro constant. That's a big number. Okay, so what does that mean? It means that if I have 1 mole of something, okay, if I have 1 mole of something, right, and that something is these so-called somethings are referred to as elementary entities. So I'm going to be referring to the term entities. And when I refer to entities, those entities in chemistry, right, in terms of chemistry and in terms of, let's say, compounds and formulas, we can either look at an atom, okay, let me add to this one, an ion. We can look at molecules. So this is if we're looking at something that is covalent, or we can be looking at what are referred to as formula units. And formula units are any ionic compound. So ionic compounds are referred to as formula units. So we have an ionic compound, metal, non-metal, as we talked about in Unit 1. And so take, for example, NaCl. So understand that at formula units, that formula NaCl is not just one Na and one Cl. It's a repetitive set of ions, cations and anions alternating. So you've got an Na attracted to a Cl, which is negative. That Cl is attracted to another Na. That Na is attracted to another Cl, and it kind of forms this crystal lattice structure. So all ionic compounds form this crystal lattice structure, and those ionic compounds are formula units. So that crystallized structure that an ionic compound are your formula units. Your molecules are anything that's covalent. Okay, so take, for example, something like water, H2O, right? We can look at that as an individual molecule, but in terms of things that are ionic, we look at them not as an individual Na and a Cl, but repeated units of NAs and CLs all in a crystallized structure. So if I take, for example, I think I have an example here. It's on my next slide. If we have 1 mole of carbon, right? What is carbon? Carbon is an atom. Okay, so that means I have this many 6.02 times 10 to the power of 23 atoms of carbon. Okay, so the entity is an atom. If I had 1 mole of magnesium chloride, it means I have 6.02 times 10 to the power of 23 formula units of MgCl. And lastly, if I've got 1 mole of carbon dioxide, I have 6.02 times 10 to the power of 23 molecules, whole molecules of CO2, right? It's molecules because this is covalent. It's formula units because this is ionic. It is atoms because this is carbon. If I want, I could put in, let's say, another one and go 1 mole of, let me copy and paste this, make things a little bit simpler for me. Let me change this. So if I have 1 mole of, let's do oxide. So I've got 6.02 times 10 to the power of 23 ions of O negative 2. Okay, so there we have it. Okay, so it all depends on what the entity is. So here in this case, this is an ion. In this case, this is an atom. In this case, they're formula units. In this case, they are molecules. Okay. Understand also, and you'll see this in the homework questions. Please, I can't stress enough how important it is to do the homework questions. These little subscripts. Okay. Let's take, for example, this formula here. Let's do this one, CO2. So with CO2, if I have 1 mole of carbon dioxide, it means I have this many, 6.02 times 10 to the power of 23 whole molecules of CO2. Okay, now, if we look at the formula, CO2, it means I have 1 carbon, 2 oxygens. These little subscripts that you see in a formula, those also represent the number of moles. So, if I wanted to look at carbon dioxide at an atomic level, and I'm looking at how many carbon atoms do I have in carbon dioxide, if I have only 1 carbon in the entire molecule, it means I will have this many carbon atoms. But if I'm looking at how many oxygen atoms do I have in 1 mole of carbon dioxide, this too implies I have double the number of moles. So in other words, when I see these little subscripts, they also represent the number of moles of 1 mole of that entire compound. Okay, so take, for example, here, one of the ones I love using, and I always call out on my bio students in the class, those of you who recognize this formula here, right? So this C6H12O6, we'll know this is glucose. So if I have 1 mole of glucose, okay, if I have 1 mole of glucose, I still have that 6.02. Okay, I still have 6.02 molecules of glucose. But if we looked at the individual atom, okay, let's look at the individual atom. Let me put it as a new bullet. If we're looking at the individual atom of carbon, okay, we have 1 mole of all of them together collectively. If we are looking at just at carbons, how many carbon atoms do we have in this 1 mole that contains 6.02 times 10 to the 23? How many of them are actually carbon? We would take this number here and we would actually multiply it by 6. So that 6 represents what are referred to as moles of something. Okay, so when you see a subscript, understand that those can also represent moles of something. So let's look at what that formula is here. And what we have here is the relationship with moles. So here is one of the formulas you're going to need to know. And this is this pyramid that we're going to use. So the uppercase N, we're using N's. So the uppercase N, the number of entities, whether they be molecules, formula units, I'll put in ions, or atoms. So we are looking for how many of that atom, how many of that ion, how many of that formula unit, how many of that molecule do we have. Little n, and here's a very important unit, because it's going to be ongoing. It's going to be one of the most common variables you're going to need to look for or solve for in a lot of the questions that we're going to see in this unit and into units 3 and units 4. And finally, N, capital N with subscript uppercase A for Avogadro is the Avogadro constant, 6.02 times 10 to the power of 23. Now, how do we, when we actually make these calculations, understand how to put this into your calculator? Okay, so a few things you're looking for. Remember, in back when we were actually at Lieberman, the lesson on scientific notation. In scientific notation, I shared with you how to type these numbers in. You're going to need to know how to put this number into your calculator. Okay, because if you type it in as a times and then hit the, type in 10 and then hit the uppercase, the subscript or the little top hat to create your exponent, you could be getting all the questions wrong. Okay, so make sure you are typing in the number as follows, 6.02, and then on your calculator, just to recap, you're going to look for either the EE, okay, or you're going to look for EXP. So you're going to be looking for one of these two buttons. And after you've typed in that button, then you're going to type in 23. You do not type the times 10 at all. This EE, okay, or this EXP, that is your times 10. Okay, so you are never typing times 10. Maybe you might be lucky enough to find a button like this on your calculator, but again, I'm not there to see what kind of calculator you have. And it could be something like this, a times 10 N button, where odds are that's what you're going to be typing in. So that's the button you're going to press, and then right after you press this, that's when you type in your 23. Okay, so please play around with your calculator. Great way to test it out. When you type, if you try to type this into your calculator, after you type it, hit equals and see, does your calculator give you this answer? So you're just typing in this number, 6.02 EE 23, hit equal. Okay, hit equal. It should give you this. If it doesn't, then you got to figure out your calculator in some way, shape, or form. Okay, so when using this formula, understand, for those who don't know pyramid, how to use these triangles, these magic pyramids, whatever you want to call them, look to see what the question asks for. If the question asks for, find the number of moles, right? Look where my cursor is hovering. Cover up that cursor, or cover up that variable that you're being asked to find. And right now, the variables that are left over is uppercase N on top of uppercase NA. That means division, because they're one on top of the other. If you're being asked to find the entities, cover up entities, notice how your little n is side by side with the NA. So the side by side implies multiplication. And we're never trying to find this one because this is an actual constant. Okay, so that constant is 6.02 times 10 to the power of 23. Okay, I have a bunch of sample problems. What we're going to do is, if you want from the video, you can pause it and try them out. I'm going to go through the sample problems and the answers. Okay, so as I go through the answers and the steps, what I do ask of you to do, just listen to it. And then my advice to you is going to be, after tonight's lesson, what I want you to do is try these sample problems on your own. Okay, so you'll see me kind of solve them all. You'll see me kind of talk about. I'm not going to go through all of them. I'll pick and choose which ones might give some issues. Pick and choose. And then what I'd like you to do is try all of them on your own. Know that you're going to have step-by-step answers followed at the end of all my slides. Okay, so let's look at the sample problems. So here are 7 sample problems that I want you to eventually work on. We're going to look at the very first one because it's nice and simple. Now, let's just get our feet wet with calculating the calculating the number of entities. Okay, so let's go right to the slide that actually has the step-by-step problems. So here is the very first question. So how many atoms are found in 0.25 moles of potassium? One bit of advice, I understand one of the biggest struggles I find with students is they kind of rush through questions. If your math skills are strong, go right ahead. I'm not going to stop you from doing it. But my advice to you is if you struggle with the math concepts, one great bit of advice is to do this, what I did here on the left-hand side. List your variable and the numbers with their units, and then list the variable that you're being asked to find. So in here, it's asking us for how many atoms. So it's asking us for atoms. The atoms of what? Potassium. Is potassium an atom? That's the one thing they need to match. And you'll see this with the second sample problem, what I mean by that. So it's asking you for atoms, and it's telling you the atom it's referring to is potassium. Is potassium an atom? Yes, it is. So nice and simple. Uppercase N is equal to little n times Na. So the only number you're really given is 0.25 moles. This Avogadro constant is what you're going to use to find the number of atoms. Okay, so we're trying to find this. So we cover this up, and it's little n side by side with Na, which is the equation that we're getting here. So when I type it in, I've got 0.25 moles multiplied by the Avogadro constant. So the Avogadro constant refers to that we have 6.02 times 10 to the 23 atoms per mole. So per every 1 mole, this is how many atoms we have. So we don't have a full mole. We actually have a quarter of a mole. So we're going to take that quarter, or that 0.25, we're going to multiply by the 6.02, and we get 1.505 times 10 to the power of 23 atoms. Now going back to way back when I did chapter 1.3, significant digits rule and the rule of decimal places. Most of these are all going to be significant digits because the calculations are all going to be multiplication and division. Okay, so in the question, we have 2 significant digits, so our answer should also show 2 significant digits as well as a unit. And the unit here for the entities, what were we being asked to find? The atoms, okay, atoms of potassium. Let's move on to the next one. Here is where some of the tricks lie, and they're not really tricks. They're just kind of, you just got to stop and really think. This is why you can't rush through the questions. So in this question, how many atoms are in 1.25 moles of water? Okay, here's the thing. It's asking us how many atoms, but it's asking us of water. Water, H2O, is not an atom. It's not an atom. But in the formula of water, okay, formula is H2O. So in that formula of H2O, I have a total of 2 hydrogens and 1 oxygen. Now, here's the thing. Here's my little n value. Here's this value. Where some students make mistakes is they stop right here. They stop right here. So when they multiply little n by the Avogadro constant, right? So they multiply 1.25 by 6.02 times 10 to the power of 23. They stop and they go, oh, I've got 7.525 times 10 to the power of 23, and they're going to say atoms of water. No, because when I do this calculation, this is based on the entire formula of water. This is based on H2O as a whole entity. That whole entity is a molecule because H2O is covalent. Okay, So we break apart water into individual atoms. So we've got the one oxygen and the two hydrogens that are connected to or bonded covalently to that oxygen. So that entire structure of H2O is a molecule. So what we've calculated is just the molecule of water. What we need to do is figure out how many atoms there are in water, and there are a total of 3 atoms in one molecule of water. So we're going to take the answer that we just found here and multiply it by 3 to further get us the number of atoms that we have in the entire structure of H2O. Okay, so it becomes very challenging looking at this in terms of big numbers like a 6.02 times 10 to the power of 23. But let's think of it as with a number that we can remember. So think of the mole, kind of like us referring to how we buy our eggs in dozen, or how we buy donuts in dozen. So what is a dozen? A dozen represents 12. So think about dozen is kind of like saying, or to say mole is like saying dozen when buying donuts. So we use the term mole to tell us that we are buying, or that we are going to have 6.02 times 10 to the power of 23 of something. Okay, so let's say we had 1 dozen water molecules. So if I have 1 dozen water molecules, it means I have 12 water molecules. But now, if in that 1 dozen, how many hydrogens do I have in that 12? Well, we know that in 1 dozen of all of this, there's 12, but I know that in this molecule of water, there's 2 H's. So this 2 multiplied by 12 gives me 24, meaning that I have 24 H's. So all we did was we took this little number here, 2, and we multiplied it by what a dozen meant. So what we're doing here is, let's say we're looking for how many atoms are there in a dozen. So if I've got a dozen, I've got 12 water molecules. But in 1 molecule of water, I have 2 H's and 1 O to give me a total of 3 atoms. 3 times the 12, that represents a dozen, okay, will give me 36 whole atoms. So what did I do? I took my 3, because there are 3 atoms, and I multiplied it by what does a dozen mean? A dozen means 12. So how does that relate to this? Well, I've got 3 atoms in the molecule of water. And in that 1.25 moles of that water, I have this many whole waters. But then I take the whole molecule that I have and I further multiply it by 3 to give me how many atoms are found in water. Let's just break this down. Let's say I only wanted to find, if I change this question and go, how many hydrogen atoms? I would take this number here and I would multiply it by 2. If I was just looking for how many hydrogen atoms are in 1.25 moles of water. Okay, and let's do one more. We're not going to do that one. It's very similar to that. Well, let's look at this here just quickly. So here it's asking us for formula units. Why? Because potassium nitrate is ionic. So it's not asking for molecules. It's asking us for formula units. Here it's asking us for atoms of silicone. Is silicone an atom? Yes, it is. Here, how many atoms are found in 5.25 moles of strontium phosphate? Strontium phosphate is not an atom, but we need to put together the formula. So here's our formula, and we identify there are 13 atoms in strontium phosphate. So when we use this formula and we get this number tells us how many formula units we have. We need to further multiply, this by the number of atoms that we have in strontium phosphate. And we get a total here of 4.11 times 10 to the power of 25. But let's look at one last one here before we move on to 6.2. How many moles are found in 5.35 times 10 to the power of 22 formula units of sodium chloride? So it's asking us how many moles. Moles is our little n. So our little n is what we're trying to find. So here are our entities. This represents our uppercase N. So, and the Avogadro constant is a given. So what we're doing is we're rearranging this formula. We're covering up this N value. We've got the uppercase N on top of uppercase NA, and we get this calculation here. So we substitute into the N. So we've got 5.35 times 10 to the 22 formula units divided by 6.02 times 10 to the power of 23. And we get this total for the number of moles. And there are 3 significant digits in our question, so our answer should also have 3 significant digits. And there you have it. Understand that sometimes if I put or typically because I'm using either regular format of writing a number or scientific notation. But one thing to make note of, the number of significant digits in both of these are exactly the same. So if you're giving me an answer and you say this or that because you're kind of iffy, is it this answer or that answer? I do deduct, especially if you show me an answer that has a different number of significant digits or is rounded off and that they aren't exactly the same. So both of these have to be exactly the same. If you'll notice here, 3 significant digits, 3 significant digits, regardless of which format I'm using. Okay, so avoid giving me this or that answers. Okay, in any calculation, in any future homework assignment or test. Because typically students give me this or that because they're like, they might be, a lot of times they're like, I don't know if I should round it to this or to that. I do deduct for stuff like that. So please don't give me this or that answers. Just give me one final, give me the final answer or let me know that this is the final answer. Okay, because it's always kind of ambiguous when I see this or this, and they both have different number of significant digits, or one's rounded differently from the other, or their units don't seem to match for some reason. You can't have this or that if they're not exactly the same. They should be the same. Okay. Any questions before we move on to 6.2? Any questions? Okay, let me get 6.2 up and running. So hopefully, like I said, practice, do the sample problems. If you go to the homework, practice the homework. I've got a ton of questions there for chapter 6 for you to work on with detailed answers. So I can't stress enough, practice, especially since a lot of us should have a little more free time now to kind of ensure that our days are lot more freedom depending on, I guess, your situation. So try to get whatever you can done in preparation, because especially at post-secondary, these concepts are vital. I've had former students, university students, come back to visit and telling me that they've got students who don't really know what a mole is, and it's pretty much the most important concept in chemistry. So going into post-secondary and not quite knowing what the mole is, kind of a very, very big problem. Okay. So anyhow, let's go into molar mass and the mole. We're ending tonight with this lesson, and we will be back again on Wednesday. I will try to post. I'll see if the if it changes to if it changes, what do you call it? The the um, the ID to enter into this class, but I'll check. Um, okay, so okay, let's start. Actually, sorry, let me just attend to a question. Let me just answer this question. Okay. So molar mass and the mole. So that little n value we're carrying over into this chapter as well. But we're going to be introduced to a new equation. Okay, so so 1 mole of carbon 12. Remember, this is isotope format. Okay, so this is the isotope format, carbon 12, means that I have 6.02 times 10 to the power of 23 carbon atoms. Okay, and that represents that in 1 mole, I have 12.01 grams of it. Okay, so what we have is, if you look at, and I'm going to just jump to this slide. If we look at the atomic masses, okay, the average atomic mass on the periodic table, remember how in chapter 3, in chapter 2, we refer to the units of those mass numbers as U units. But now let's ignore the U and let's look at them as representing how many grams for every 1 mole. Okay, so if you look at the periodic table, you'll have, so take for example hydrogen. So if you add 1 hydrogen atom, that 1 hydrogen atom, if I was to weigh out, okay, let's do some really quick math here. Let's look at the formula H2O. Okay, so let's type this in up here, H2O. Okay, so I've got the formula of water here, H2O. So it means I've got 2 hydrogens, 1 oxygen. So to calculate the molar, to calculate the mass, so if I asked you, give me a beaker filled with exactly 6.02 times 10 to the power of 23 atoms of water, how would you go about measuring that? You're not going to sit there and try to count. That's impossible to count out each individual atom. Even if you thought you pick up a drop with a dropper, there's many water molecules, even in something as little as a droplet of water. Okay, so how do we do that? We utilize these atomic masses, but we refer to the masses instead of U units as gram units. So if we have 2 waters, right? Sorry, 1 water molecule, 2 hydrogens. Each hydrogen is 1.01 grams. So if I've got 2 of them, I'll have 2.02 grams of just hydrogen. I'm going to add it to 16 grams. Okay, because each oxygen is valued at 16 grams for every 1 mole. And if I added these 2 together, this would work out to 18.02 grams. So what this 18.02 grams means is that for every 18.02 grams that I weigh out of water on a scale, it will be equivalent to exactly 1 mole. So on that scale, if I weigh out 18.02 grams of water on that beaker, technically that beaker will contain exactly 6.02 times 10 to the power of 23 molecules of water. Okay, so that's what we're using. So we're using those values as gram units for every mole. Okay, so here is so the mass of 1 mole of any element is expressed in grams, is numerically equivalent to that average atomic mass of the element. So we're using those mass numbers as molar mass units. Okay, so molar mass units. These molar mass units are the values of those average atomic masses added up in a formula. Okay, so make sure you know your formulas. Okay, so remember how we were saying about referring to your, I guess, your notes for a future test or a quiz. These equations you should be able to pop up. The only thing you might need to look up is going to be, look on the periodic table. Where do I know these numbers? If I have to look through my notes, okay, what is molar mass again? You're not properly prepping for this course. Okay, so understand that when it comes to the evaluations, I'm going to be, you've got to be on top of the material as best as you can, because even though you have that open book, don't rely on it, because like I said, I'm going to be very very picky about making sure my evaluations do come in within the time limit, and I will not be taking any evaluations after that time limit, because I struggled with, if the struggle is got, you've got to fix that struggle well ahead of time, because open book, I'll take my time, I'll take 2-3 hours to complete a problem. These problems shouldn't take that long to do. Okay, and if it does, it means that there's a lot of content that you're not quite getting, that if you're constantly having to flip through notes and whatnot in order to know how to move on. Okay, so a great test would be to do those practice questions. If you're not doing those practice questions, like I said, all my evaluations will be no different to those type of sample problems. In fact, my homework questions, some of them are actually going to be even more challenging than the type of questions I'll give on a test or a quiz. So please, I can't stress enough, make sure that you stay on top of the material. Anyhow, here's our new pyramid for the formula. So mass, moles, and molar mass. Understand that molar mass, we use the uppercase M. So uppercase M equals the molar mass. Mass, the units for mass, that is in grams. And mass, the variable is little m. Okay, little m represents mass. So little m represents mass, big M represents molar mass, and of course, the number of moles is lowercase n. So there's just another example of gold. If you looked at 1 mole of gold, so you want to weigh out exactly 1 mole of pure gold. Well, if you're able to weigh out 196.97 grams on a scale, you will have exactly 6.02 times 10 to the power of 23 atoms of gold that you've just, I guess, isolated, if you can put it onto a scale. Okay, molar masses are rounded to 2 decimal places. If you're using my periodic table that I provided for you, those 2 decimal places are already there rounded for you. Okay, so you're using the molar masses exactly as they appear on my periodic table. Okay, let's look at the sample problems. Okay, so some sample problems as simple as using tonight's or this lesson's equation. Some require you to go back and use the Avogadro. So understand that sometimes when you get an equation, and this is a great tip for anyone who's planning to take physics, see how um, equations kind of relate to one another. Okay. If you see certain variables that are common in multiple formulas, understand that they can interact with one another. You can easily substitute um, the other equations with one another. Okay. Anyhow, let's look at the very first one here. Determine the molar mass of ammonium phosphate. So one of the important steps to get full marks is to be able to put together that formula. So here is the formula of ammonium phosphate. So in total, we have 3 nitrogens, we have 12 hydrogens, we've got 1 phosphorus, and we've got 4 oxygens. So we look at the periodic table, we look at the molar mass of just 1 nitrogen, and that 1 nitrogen is 14.01. So we're going to multiply that by 3 to give me this, 42.03. We've got 12 hydrogens, and 1 hydrogen is just 1.01. So take that 1.01, multiply it by 12 to get 12.12 grams per mole. Okay. We have 1 phosphorus, so 1 times 30.97. You don't have to show this. You can go straight to this. And then lastly here, we've got 4 oxygens, so 4 times 16 to give me 64 grams per mole. And then all we're doing here is we are adding all this together to give me a grand total of 149.12 grams per mole. Typically, when we round, we always round based on the least number of significant digits. But because there aren't, the rule of thumb is this: always round. If there is no number to refer to, always round to 2 decimal places. And that's why our answer is 149.12 grams per mole. Okay. In the event of a question like this on an evaluation, if it's worth 2 marks, typically 1 mark is showing me the steps. You can kind of go straight to finding this, but because the question is actually asking you for this as your final answer, I want to see the steps on how to go about getting to that problem. But in a question like this here, sample problem number 2, because the question doesn't ask us for the molar mass, it's actually asking us for the mass. It's asking us for little m. So in that case, here is the big M. This is the molar mass of potassium oxide. Potassium oxide is K2O. Again, if you don't know how to put together this formula, you got to fine tune your chapter 4 content. Okay, your ability to put together formulas is vital if you want to get full marks. So this answer is based on breaking this down and finding the molar mass. But because I'm not asking you to find the molar mass of this formula, I'm actually asking you to find this. You can go straight ahead and figure this out on your calculator and just type out the full answer. But in this question here, I actually specifically ask you to find the molar mass of a formula. So I want to see the steps to solving it. But in this case, you can go straight to the answer. Don't forget your units. Let your units work for you. And I should have shown you here where they cross out, but the moles here cross out, leaving us with gram units. So the answer works out to 23.55 grams, but we only want 2 significant digits. So the answer works out to 24 total grams. Okay. Let's look at the next problem here. The number of moles again. Now this time here we were asking for the mass. So cover up mass. We've got moles multiplied by molar mass. Okay. In this case here, little n is equal to, so we cover up little m on top of big M. I always think of it as the little m piggybacking on big M, right? So we find the mass, we divide it by the molar mass, we get the number of moles, and then we round this answer based on the number of significant digits in our question, and that works out to 4 significant digits, and our answer works out to 0.1584. Okay, let's see if we interchange, if we utilize one of the other. No, we don't. So all the formula, all the questions kind of work the exact same way. So here in this case, we're being asked to find the mass of something. So we're being asked to find little m. We're given little n. Typically, I don't give you molar mass. Okay, molar mass is something you're typically going to be calculating. And how can you go about calculating? Well, you need to be able to put together the formula. So technically, if I give you the name of a compound, your ability to find the molar mass is how you would find this big M. Okay, so that's the one thing you're going to notice. Big M, notice in this one here, big M, I don't give you big M, but big M is to be calculated. Well, in this case, it's actually asking you to kind of figure out what it might be. But in all the questions here, question 4, question 3, question 2, you're being asked to find the molar mass, but notice in every single one, you've been given the formula name, in which case you're able to put together the formula. Okay, so please do the practice problems. There's some more practice problems at the end of where you're going to mix and match. I guess you're going to be using both equations. The equation from chapter 6.2 to fill these out, and chapter 6.1 to complete this part of the table. So this number of particles, that's your uppercase N. Mass, right? This is our little m. Number of moles, this would be our little n. Actually, let me put little n here. And molar mass, this is our uppercase M. Okay, so please go through the sample problems, do the homework questions in preparation, because a lot of the stuff that we're going to see, especially here in 6.2, this carries over. Your ability to find molar mass, your ability to find this and find this will be ongoing. These 3 things typically are going to be ongoing throughout this this unit and into the latter units as well. Okay, so I'm going to end our recording session. I will be answering any questions after I stop the recording. I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.